All right, hi. My name is Howard, and this is Alessandro. We work together. And today my talk is going to be on formally verifying a zkVM. For those of you who may be new to the field, I wanted to start by talking about what formal verification itself means and what it aims to achieve. Behind every formal verification system starts with a formal verification expert, like Alessandro. And what the formal verification expert is trying to do is to construct, using a theorem prover, a model, a representation, a concept of the system that is being studied, and pursuing properties that you would like to test for and check against to give yourself strong mathematical guarantees of soundness. Now, this can be applied in many different forms. I think many times you can break it down into two forms, hardware-based systems and software-based systems. The requirements can sometimes differ in terms of what you're trying to look for in each, but the end goal is always the same. And for instance, in a hardware-based system, you might be trying to check for the correctness of a flow of, say, a RISC-V chip and one of its opcode sequence, and the way that it processes is being performed correctly. And that's kind of one example of a formal verification in the hardware sense. On the software side of things, oftentimes you're trying to check for some form of completeness or soundness about a piece of a code or a behavior of code. For instance, if you have a compiler and you want to write a new pass in your compiler, you want to make sure that under all circumstances or all inputs that this pass will behave in the expected form or pattern there. And so this is kind of a way to really try and mathematicalize and formalize your notion of what you're building. So as I've mentioned, there's a correctness property here. This is what you're really testing for, and that property is effectively what you're trying to evaluate on. Now, based on what the theorem prover says, you can get one of two possible outputs. One could be a green check that says, hey, this proof of theorem is correct. But it's more nuanced than that. It's not just a simple green check. There's honestly much more to it. You want to really dive in and understand what it is that it checked and to what level and to kind of what extent the check was complete. But I think one thing that's worth noting here is that this type of a check, this type of a guarantee is much stronger than many other techniques that you may have heard of. Some of you may have heard of, for example, fuzzing, where you run a fuzzer and you have it kind of give just a random set of inputs, random in, random out, and you let it run overnight, or you let it run for a week, and you give yourself some level of assurance with fuzzers that the system behaves as intended. However, what makes formal verification so much more powerful, and why this proof becomes even more powerful, is that you have a much higher assurance than this type of fuzz testing. So you can now address cases that are really sampling for all types of integers, or for all types of variables, for all types of circumstances, and that gives you a strong assurance. It can also be used to justify complex optimizations and also suggest new optimizations. So for example, for those of you who have dabbled a bit in formal verification, you may be aware that if you're trying to formally verify an R1CS circuit, oftentimes you might actually realize by running this that, yes, my circuit is constrained correctly, but I actually have over-constrained, and I can actually reduce some of my constraints. And these models are actually quite useful with the eye and interpretation of a formal verification expert to identify that. Now, on the contrary, let's say that the theorem prover errors out, it fails. What do you do then? Well, unlike how many of the talks here on ZK proofs have gone, it's not just the simple false. Like it's not just going to come out and be like, it's a little more nuanced than that. You have to go through and actually parse and understand, again, with an expert, why the proof itself is not working. And this process of discovery is actually how you go to kind of remedy and find the bugs in the original implementation. In the process of discovering this with a formal verification expert, you tend to reveal and find new bugs. And so that effectively is an overview of how formal verification works as a system here. Now, myself and Alessandro and many of our team members who are here today, we all work on a blockchain called Aleo. And some of you have heard of it, some of you haven't. I thought it'd be useful to talk about formal verification in the context of a blockchain like Aleo. Why? Because Aleo is a zkVM, and just to help paint the picture for you, I often like to use this graph of programmability and privacy, where Bitcoin is quite low on both. It's just a coin, and it's pseudo-anonymous, right? So it's not fully private. Ethereum said, let's take that idea and add some programming to it, and so you ended up with high programmability. Zcash said, let's go the other direction and extend Bitcoin to offer full privacy, so extending that pseudo-anonymity into full anonymity. And now there's this upper right-hand quadrant of saying, well, what if you could achieve that full level of privacy, but also have the programmability of Ethereum, aka private smart contracts? That's the holy grail. That's the kind of goal that we wanted to build and achieve with Aleo. And so this graph is meant to illustrate that. Now, based on what I just described, you can probably imagine that there is a myriad of potential risks in building a system like this, because you are now building a general purpose VM that is being proven mathematically using zero-knowledge proofs, using circuits and constraints under the hood. And so to really give you the level of assurance that this is working and this works, especially with privacy, you want something like formal verification. And so to give you a sense of all the parts where things could go wrong, this is an illustration of the actual dev flow, of the actual user flow from top to bottom. User comes, provides some Leo code. Alongside it, they provide some public and some private inputs. That then gets operated on and run via dev tools. Specifically, the program is compiled into AVM bytecode, and you get out these public and private outputs, and you get out this zero-knowledge proof, this proof of an off-chain execution. You've ran your code, your smart contract code off-chain. And in addition, your contract might say, hey, in order for me to finish, I need to settle on-chain. And when you go to settle on-chain, there's some settlement logic that you need to finalize as well before it fully lands in a block. And so this is kind of every arrow that was illustrated here is a potential point of failure. And so we wanted to formally verify as much of this as possible. And yeah, more so, once you've done all that, then you need to submit it to the blockchain, right? So the AVM bytecode on the left gets sent via a deployment transaction. It's like deploying your contract on any blockchain. And then over here, you have the verify and the execute pieces. So you need to verify the proof of your off-chain computations. And to settle, you have to run a small bit of code for settlement. And that's this execute piece, which, again, lands in a block. So you may be wondering, why apply formal verification to Aleo? Well, I've already started to prime you and give you some of the answers. But to make it very concrete, bugs in blockchain software can lead to, for instance, the creation or destruction of currency. And as we all can agree, the soundness of your money minting system is pretty important. I see some thumbs up there. But even more so, we're talking about a chain that actually is going to offer users privacy in their accounts on-chain for the first time. And so for their program privacy and for their program data, they may not want to make it available and revealed to everybody. And so a loss of data privacy or integrity would also be detrimental to a system like this. And for the cryptographers in the room, I think you can also come to understand that a lot of teams, especially in this room, are working on new ZK circuits. There's I hear and see new circuits being built day in, day out. And under-constrained bugs can be particularly pernicious. You may ask, what are under-constrained bugs? This is a bug where you expected the adder to take in two variables, x and y, and spit out the value z, being the sum of x and y. But maybe you forgot to think about overflow and underflow behaviors to make it safe. In that case, you would have under-constrained because you didn't provide the necessary checks, the value checks and balance checks to reflect for the case of when that happens. And so these are the types of models that you tend to run into and tend to get caught fairly quickly when you're using a formal verification a method to kind of formally prove the correctness of that circuit. So that is kind of what under constrained means. Now you can fool a verifier to accept the fake ZK proof then with that technique. If that overflow bug exists, I could exploit that and then convince someone that I actually had all this money when I didn't have all this money. That would be very bad. But I think the bigger problem, and as many of you know, is that as an industry, a lot of teams in ZK are moving fast, and shipping fast. And these are bugs that are very hard to test for. And to make sure that you actually catch these bugs, there's very few techniques that get you that strong level of assurance. We alluded to fuzzing, but in reality, formal verification is probably the most surefire way that we know of today to actually detect these types of issues here. And so formal verification can prevent that. And in order to demonstrate that, I'd like to hand it over to Alessandro for him to walk you through a few examples of how formal verification applies in Aleo. I think you have a mic. Here's the clicker though.
All right, can you hear me? Yes, good. So formal verification can apply to different parts of the Aleo ecosystem. Here's a notional flow, let's say, of data. One writes an Aleo application, uses development tools to build transactions that include zero-knowledge proofs, finalization code, etc. And that gets deployed to the Aleo blockchain. So there's a lot of components here where you can apply formal verification. One is to check application properties of Leo programs. For example, is the program secure? Is it leaking information? Is it doing the right thing? Things like that. Development tools, they do compilation of chain execution, zero-knowledge proof generation. So do they do that correctly? So do they preserve the semantics of the Leo application, which is what the user is writing things, the smart contracts in? And also in the blockchain itself, there is a consensus layer to organize the transactions into blocks. There's the mechanics of zero-knowledge proof verification, on-chain execution, and so on. And those, for example, for consensus, we want to show liveness and safety properties. For zero-knowledge proof verification, on-chain execution, we want to show correctness. Is it doing the right thing? So that's where it applies. So to date, we have applied these techniques to some of the components. And so initially, we worked on the Leo language. We formalized its syntax and semantics. It was for an early version, so we need to update it. But it was complete at the time. And we also developed a tool to generate theorems every time the compiler runs for just the initial phases of the compilation, so like parsing and what you call canonicalization. And we did find bugs in the parser in that way, so that was useful. Later we moved to the zero-knowledge circuits that Howard was describing. So what we did is formalizations and verification of a good number of the operations of the circuits in our blockchain that implement operations. And we did find both bugs and optimizations in the process. More recently, we worked on the consensus layer, the BFT, AleoBFT protocol. We formalized the protocol, verified the main property, which is blockchain non-forking, and we're extending it towards other properties. And we also found some bugs and some optimizations. So let me give you some details about the last two, the circuits and the BFT. So here's a super simple example of a circuit, which is in R1CS, because that's what we use. What does it do? It's a division. The X and Y are the inputs and outputs, and Z is the output, it is the quotient if Y is not 0. Otherwise, it's an error. So for this, we want to prove two properties for this kind of circuits. One is soundness, which says that every solution to the constraints corresponds to a non-erroneous computation. And the other property, the converse, is completeness. So for every non-erroneous computation, there is a solution to the constraints. So another super simple example of a circuit that is actually wrong is the one for positive square root. If you write the circuit like that, it's under constraint. That's what Howard mentioned before, which is a problem. So we try, because it allows a negative root. So we cannot prove soundness, it does not hold, and when we do the proof, we discover why. Oh yeah, because there's another solution. Incidentally, completeness still holds, but you need both. Now, briefly, hopefully it gives you the flavor. The circuits are more complicated, the ones that we did, but this is a simple example. So the consensus protocol here, there's a number of validators. Some are correct, some are faulty. The red one is faulty. They achieve consensus, and our protocol starts from the existing Narwhal protocol, which serves to partially ordered transactions into a DAG. If you can see the top parts of the green boxes, there are little DAGs. That's what they agree on. And then there's the Bullshark protocol, which locally linearizes the DAGs into blockchains. And that's the lower part. You see the little blockchains there. But then we made some significant, I mean, the whole team, Aleo and Provable, made significant extensions, which was one is that the validators are dynamic. So they can change potentially at every block, even though usually they don't, but they could. Also, we use stake and not just numbers of validators. And then there's also a phase of syncing. When a validator comes up, it has to sync, and there's some subtle issues there for correctness. So what we did here is that we formalized the protocol as a label state transition system, like an infinite state machine, and we proved properties, mostly in the form of invariants, which say that the invariant holds initial state and is preserved in every state. The main thing we proved, which involved quite a bit of work, was to show that the blockchains never fork. So essentially, if you have two correct validators, they have their own copy of the blockchain. So sometimes they have the same blockchain. That's fine. That's perfectly good. One may be a little ahead. That's okay. That can happen. But they cannot be incompatibly ahead of each other, so they need to, so that would be wrong. And so we proved that for every reachable state from the initial state, you will never end up in a state where they have forked. So blockchains never fork. That's the formula, just if you're interested. More information, there are some papers. If you want to take a picture, you can go on my webpage, just look up my name, and you'll see it there. And with that, I will give the mic back to Howard, who has a call to action.
I think we're out of time. I think as a just finishing thought for those who are interested to give this a try, there's the Leo Playground. It's play.leo-lang.org. Obviously, Aleo is at aleo.org, and Provable, which is the Aleo Labs company, is at provable.com. Go check out our Twitter as well. But with that, I'm out of time. Thank you very much.
It's good, man.